Hello and welcome to this third video on the theory of special relativity. In this episode we will be focusing on the nature of simultaneity. The objectives of this video are to derive, understand and use these two equations. In the left one, t prime stands for the time in a stationary frame of reference, while time t stands for the time at position x in a frame of reference that is moving to the left of the stationary frame of reference. The second one is the other way around. T is the time in a stationary frame of reference and t prime is the time at position x prime in a frame of reference with a relative velocity to the right. Besides that, we will be able to fully understand the coherence between simultaneity and length contraction. Useful prior knowledge. To be able to follow along properly, I will put two links at the top of this video. Before you continue, be sure to watch the first video on this subject, the one on time dilation, and the second one on length contraction. As for the standards, all speeds are 0.6 c, like the previous videos. And when considering the Earth to be stationary, an S will appear in the bottom left of the screen. When the spacecraft is stationary, an S prime will appear in that corner. The theory of special relativity only concerns itself with motion in one dimension. That means all objects move along one single line. We could display such a situation like this, but it will become unclear very quickly. So I've moved the objects apart to be able to view all aspects of the animation. But remember that their actual location is located along one line. The definition of a snapshot. Let's use this animation as an example. At this point, all clocks according to an Earth observer will display these values. But if there was a human on Earth actually looking at the two other clocks, they would see a value from the past due to the fact that the light from those clocks has to travel across space, which takes time. A human would see the satellite display 0.4 seconds, since its distance from Earth is 0.6 light seconds. And they would see the spaceship further to the left with a display time, in this case of 0.5 seconds. But in this video we will not be considering what a human sees, only what the clocks themselves are actually displaying. Then distances in this video are not fixed, and when they are significant enough I will mention them individually. Also, the spaceship's reference point changes throughout the video, either tip of the fuel tanks or its exhaust, and when significant I will mention where the reference point is. And finally, all animations are played at a quarter speed. My disclaimer states that all motion of objects are to scale, but the size of the objects themselves are not. In this first animation we will discuss what two simultaneously running clocks are and how to establish such a setup. We will again use the characteristics of light to do this. To get this done we require two identical clocks placed at different locations in our own frame of reference. And it is important to know how far apart those clocks are. In this case, the distance is 1920 pixels, or your entire screen. Exactly halfway between the two clocks, we will place two laser pens, one pointing left and the other one pointing right. The laser pens are rigged in such a way that they are triggered simultaneously, and they will both have a blue photon shoot out at exactly the same location. Again, right in the middle between the two clocks. I will refer to these as synchronizing photons. When the photons hit the edges of the screen, this is where the clock's triggers are located, the corresponding clock will start counting. We see that both clocks start at the same time, and since neither of them is moving, we can see that both clocks run at exactly the same pace. All thanks to the fact that the speed of any particle of light is c, from our perspective. Next, we will place the synchronizing system in our spacecraft. Now our spacecraft's length is equal to half a light second and its reference point, So the point from which we measure all x prime distances is located on the left. The following events are similar to the ones we have looked at in the previous videos. So Earth to the left and the satellite to the right. The Earth and satellite are stationary in relation to each other, so they exist in the same frame of reference. The relative speed between the spacecraft and the Earth's frame of reference is equal to 0.6 c. In the previous video, the one on length contraction, we found that distances that are parallel to the relative motion in the Earth's frame of reference have shrunk in relation to the spaceship. In this case by a factor of 0.8. Now we want two events to happen at the same time and place. The first, we want the Earth's clock and the spacecraft's left clock to hit each other while the other event occurs, which is the left sinking photon hitting the spacecraft's left clock. This will trigger the start of the Earth's clock and the left clock on the spacecraft, while the sinking system starts both spacecraft's clocks simultaneously. Now the challenge here is not to discuss how we can make those two occurrences happen at exactly the same time, but we will assume that they happen at the same time and draw our conclusions based on the consequences. So, at a certain moment in time, the synchronizing photons shoot out and reach the left and right clock simultaneously. At the same moment, the Earth's clock will reach the spacecraft's left clock. All three clocks will start counting. Our spacecraft's clocks will run synchronized and the Earth's clock will start at the same time, but it will run slower from our perspective, as we have discussed in the first video. Note for a second here that I have chosen the length of the spacecraft and the distance between the Earth and satellite such that the right photon hits the right clock just when the right part of the spacecraft hits the satellite. We will come back to this fact later on. On to the next step. This is the same situation as the previous animation, but this time we are viewing the flow of events from the perspective of the Earth. So the measurements between the Earth and satellite are back to their own length, but now the length of the spacecraft is contracted. To satisfy the fact that we see the same events happen as in the previous animation, we will find that the left synchronizing photon reaches the spacecraft's left clock at the same time as the Earth does. Let's for a second go back to the moment where the two photons leave the middle of the spacecraft. Note that from our perspective, the speed at which they travel through the spacecraft is different. The right sinking photon might seem to move slower than the left, but in actual fact their speeds in relation to us as a viewer are identical, the speed of light. You can see this by holding your finger at the screen where the photons originate. We now have Earth's clock start at the same time as the left spacecraft's clock, and we have the two spacecraft clocks running at a rate of 0.8 compared to our clock. Now remember, we created a system to synchronize the two spacecraft clocks, but that synchronization only counts in the spacecraft's frame of reference, because to us those two clocks do not run simultaneously at all. Now our Earth clock runs at the normal rate. The spacecraft's left clock starts at the same time as ours, but runs slower by that factor 0.8. And then there's the right clock. The right clock will run at the same rate as the left clock, so a factor of 0.8 of the speed of our clock, but it has started at a later point in time. This concept where the terms synchronized and simultaneous are dependent on the frame of reference is the basis of this video. Next we will find out what the difference in time of the left and right clocks is and derive a formula for this. To do this, let's first define the length of the spacecraft. We will call this x prime. Since the spacecraft is contracted from our point of view, the length according to us is x prime over gamma. Next we want to find out what distance each photon should travel before triggering their respective clock. This distance is x prime over 2 multiplied by gamma. Then we need to establish the speed at which the photons shoot through the spacecraft. The left photon approaches the left clock at c plus v, or in this case 1c plus 0.6c equals 1.6c, while the right photon approaches its clock at a speed of c minus v, or 1c minus 0.6 c equals 0.4 c. To find the time it takes each photon to reach their respective clocks, we divide the distance, x prime over 2 gamma, by the speed, so either c plus v or c minus v. So the left photon will travel for x prime over 2 gamma c plus v seconds, while the right one travels x prime over 2 gamma c minus v seconds. We want to find the difference between these two times, and since the time taken by the right photon is greater, we will want to calculate TR minus TL, which is the time of the right photon minus the time of the left photon, and that equals this. Equalize the numerators by multiplying the left fraction by c plus v over c plus v, and the right one by c minus v over c minus v. This will yield this. The middle terms in the denominator cancel out, and we are left with. Now we can subtract the numerators to get this. And we can cancel out the 2 in the numerator and the denominator. Now in the denominator I will factor out c squared to get the following. Now watch how we change what is inside the brackets in the denominator to be exactly gamma squared. So we could rewrite this to be, we can simplify to get this. And this is the time difference measured on Earth between two clocks in another frame of reference which are a distance of x prime apart. We can also consider the answer as follows. It is the time difference between the start of the left and right clock as shown by an earthly clock. So what will be the time difference as displayed by a moving clock? Well, think of it this way. If our clock shows gamma x prime v over c squared at some point, the spacecraft's left clock will show us gamma x prime v over gamma c squared, which equals x prime v over c squared, since our clock and the left clock started at the same moment, but the left clock runs slower. We will use this equation as follows. The clock at location x prime starts x prime v over c squared seconds later than the clock at location 0, the spacecraft's reference point. Now to find the time which our Earth clock should be displaying, we take the spacecraft's time of a clock at location x prime and we will call this t prime. First we want to work back to what a clock would show us at the reference point, so at x prime equals 0. To do that, we take t prime and add the time difference of the two clocks, so t prime plus x prime v over c squared. Now we have the time of a clock at the spacecraft's reference point. To convert that time to our own time, we only need to multiply by gamma, which we can show as t equals gamma multiplied by t prime plus x prime v over c squared. And if we fill in what we see here, realizing that the own length of the spacecraft equals half a light second, we get t equals this, and the two c squareds cancel out. So we get this, and simplify will be 0.6 seconds. Let's prove the same formula for a situation where a frame of reference moves to the left of an observer's frame of reference. We will be sure to add a synchronizing system as we did in the previous animation, but this time to the clocks on Earth and in the satellite. Distances and reference points are the same as in the previous two animations. Again, we will find that the time it takes for the sinking photons to reach their clocks differ if we look at this system from the spacecraft's perspective. the photon traveling opposite to the satellite's motion, so the right synchronizing photon, reaches the satellite's clock sooner than the left photon. Analogous to the previous animation, we will call the distance between the Earth and satellite x. As perceived by us in the spacecraft, this length will be x over gamma. This time around, the left photon will travel for a longer time than the right one, so in order to find the difference we will subtract Tr from Tl, yielding the same result as the previous calculation, through precisely the same reasoning. Because we're viewing these events from the spaceship, the time difference on the Earth's clock is smaller, or dilated, compared to the time difference on our own clock in the spaceship. That's why delta t prime is this, while delta t is that same quantity divided by gamma, or x multiplied by v over c squared. To find a relationship between a clock in a moving frame of reference at location x, we need to take the time we see at that location and subtract from that the value x times v over c squared, to adjust it to the time that we would see at the reference point. The time we are then left with needs to be multiplied by gamma in order to find the time that our own clock is showing, or t prime equals gamma multiplied by t minus xv over c squared. Note the only difference with the previous result is the minus sign instead of the plus sign. This is only because the relative speed is in the negative x direction from this point of view. This and the previous animation is one way to establish a difference in simultaneity between different frames of reference. In the next example, I will use a different approach to derive the same formulas. We will be looking at a spaceship, the Earth and a satellite, but note that their measurements will change from the last two animations. Also, the reference point of the spacecraft will be back to the tip of the fuel tanks. Let's take a look at the animation we showed in the beginning of the video on length contraction. The distance between the Earth and the satellite is now 0.6 light seconds, and the reference point of the spacecraft is back to the tip of the fuel tanks. The length of the spaceship is less relevant for the time being. We found that the spacecraft hits the satellite after traveling for 1 second. However, at the moment of that event, the spacecraft's clock had only run for 0.8 seconds. Let's look at this flow of events from the other side and see what we find. For simplicity, I've left out the satellite's clock for this animation. If we rerun the events, it seems like the spacecraft hits the satellite after 0.8 seconds, as we saw in the previous animation. But now, if we look back at the Earth's clock at the time of this event, we see it displaying a time of 0.64 seconds, where in the previous animation we would expect it to be 1.0 seconds. The 0.64 seconds is the time we come up with when dividing our own time by gamma. So apparently, if viewed from the Earth, the spacecraft hits the satellite when that clock is shown 1 second, and the spacecraft's clock is showing 0.8 seconds. But if viewed from the spacecraft, the event takes place at time 0.8 seconds in the spacecraft, but only 0.64 seconds on Earth. So we can conclude that simultaneity depends on the frame of reference from which you watch an event take place. To Earth, the 1 second, 0.8 seconds, and the spacecraft hitting the satellite occur simultaneously, while to the spacecraft, the times 0.64 seconds, 0.8 seconds, and the collision occur simultaneously. I will display the same animation now, but instead of only showing the movements in a single dimension, we will now move both frames of reference vertically as time progresses. This way we can visualize the difference in time as well as the movement in space. So for every second that elapses on Earth, we will set a tick mark. That is the time displayed by the Earth's clock when it passes that position vertically. Now if we forward to the point where the event took place of the spacecraft hitting the satellite, we can draw a horizontal line indicating that everything that happened simultaneously occurred on that horizontal line. If an Earth observer were to take a snapshot at that time, all occurrences on that line would be captured in that snapshot. Be aware of the fact that this horizontal line only indicates simultaneity to an Earth observer though. For the spacecraft, we found that its time was showing 0.8 seconds, while the Earth's clock displayed 0.64 seconds. So these two moments must have been happening simultaneously to a spacecraft observer. We can therefore display the spacecraft's simultaneity with a slanted line in the so-called spacetime of the Earth's frame of reference. First off, drawing a line from the spacecraft down to the one-dimensional space of the Earth and satellite, representing the actual location of the spacecraft. Then considering the fact that the following two occurrences happened simultaneously to an observer in the spacecraft. So the 0.8 seconds point in the spacecraft and the 0.64 seconds point on Earth. Then, a straight line between these two moments must represent simultaneity to the spaceship's frame of reference, S'. We can now note that if an observer in the spacecraft were to take a snapshot right now, they would capture everything that happened along this slanted line. Let's go back in time for a second, just to show that the gradient of this line is constant, regardless of the elapsed time. At every stop of the spaceship, the slanted orange line will connect the spaceship's position and time with its observed time on the Earth's clock. For the spaceship's time of 0.2 seconds, they would see an Earth's clock display 0.2 over gamma, or 0.16 seconds. For 0.4 seconds, they'd see 0.32. And 0.6 would yield 0.48, and so on. When we walk through a few random moments in time, we find that the gradient stays constant. To find a relationship between the time t at location x and the spacecraft's time t prime, we will first need to find the gradient of this line. So let's start off by finding what the difference in the vertical axis is. We have time t at the top, time 0.8 showing at the spaceship, which is t over gamma, and time 0.64 seconds below it, which is in actual fact t over gamma squared. The difference between the top and bottom is equal to t minus t over gamma squared, or t multiplied by 1 minus 1 over gamma squared. If we work out gamma, we will find t 1 minus 1 plus v squared over c squared, or tv squared over c squared. Now that we have the vertical value, let's find the horizontal value, or the distance that the spaceship has traveled between the two events. As we have discussed earlier, that distance is equal to vt. So to find the gradient of the line, we want to divide the vertical value by the horizontal value, and we will find the amount that this line goes up vertically per horizontal unit that it goes to the right. So tv squared over c squared divided by vt equals v over c squared. If we want to find how much the height of this line is increased, we need to multiply this gradient, v over c squared, by the distance it has traveled to the right, which is x. When we do that, we get xv over c squared. In other words, when an observer in the spaceship looks at a clock at position x in the Earth's frame of reference, we know that the time displayed on that clock is xv over c squared more than the clock at the origin, or at x equals 0. To finalize the relationship between t prime and the value x, let's look at this. If a spaceship observer was to look at the Earth's clock at x equals 0, we know that we can multiply that observed time by a factor gamma to find our own time, or 0.64 seconds multiplied by 1.25 equals 0.8 seconds. But if we observe a clock at position x, we need to first subtract xv over c squared from that time and then multiply it by gamma to find our spaceship's time. So t prime equals gamma t minus xv over c squared. Exactly the same formula that we found in the previous setup. If we view these events from the other frame of reference, so from the spaceships, we will find almost the same relationship. Quickly walking through an identical setup as the previous animation, we can use the same reasoning to find the vertical distance that our slanted line covers. For every meter x prime, it moves to the right.
resulting in a line according to x prime v over c squared, but this time the gradient is negative. If we are an observer on Earth looking at the spacecraft and we want to calculate the time on Earth, while looking at a spaceship's clock, so its time at x prime equals 0, we do the following. Multiply that x prime equals 0 time of the spaceship by gamma to get t equals gamma t prime. Now if we view a clock at another location in the spaceship's frame of reference, let's use x prime, we again need to convert that time to what it would be at the spaceship's origin. This time around we need to add x prime v over c squared, which by the way is the same as subtracting negative x prime v over c squared, because of the negative gradient of that slanted line. Through the same thought process we will end up with t equals gamma t prime plus x prime v over c squared. Let's work out an example. First off, let's discuss which formula to use in which situation. Now since the t equals gamma t prime plus x prime v over c squared formula is derived from the Earth's point of view, we want to use that formula when considering occurrences that are observable from that frame of reference, so from the Earth. And remember that time t from this formula prevails in the whole frame of reference S, since we assume that all clocks are synchronized. The other formula, t prime equals gamma t minus xv over c squared, was derived from the point of view of the spaceship, so use it when considering observations from the spaceship's frame of reference S prime. Also, time t prime is the same for every position in S prime. If we want to calculate at what time the collision between the spaceship and the satellite took place, according the Earth and satellite, we must use t equals gamma t prime plus x prime v over c squared, as previously discussed. Since the collision is an event, all observers will agree that the spaceship showed a time of 0.8 seconds when that happened. Now the x prime location of the clock was equal to 0, so filling that in the equation will yield 1.25 multiplied by 0.8 equals 1.0 seconds. Let's go back to the point where the clock started, but now we will also put the clock back on the satellite. When playing the animation now, we understand why the time of 1.0 seconds in the frame of reference of the Earth and satellite makes sense. This is the end of the second derivation of these formulas. Next will be the purely algebraic derivation. In the previous video we used this display to derive a formula. Now we will use the same setup to derive the formula that we previously derived in this video. Considering the left frame of reference, we can find that x equals gamma x prime plus vt prime. And looking at the right frame of reference, we'll conclude that x prime equals gamma x minus vt. Let's take the first formula and move gamma to the other side to get x over gamma equals x prime plus vt prime. Now we will move x prime to the left, then divide by v will get us. Now let's substitute x prime equals gamma x minus vt, the second equation from the beginning. Next, factor out gamma on the left side and split the second fraction. Work out the gamma squared that we have created. Work away the brackets shows us the x over v terms cancel out and we are left with gamma t minus x v over c squared equals t prime. To find the formula for t, the process works similarly, but we need to start with the other equation. Same steps will apply, so we will get gamma t prime plus x prime v over c squared equals t, of which both will agree with our previous derivations. To wrap up what we've been talking about, the most important point is to be able to use the formulas correctly. So for filling in times that occur simultaneously according to frame of reference S, use gamma t prime plus x prime v over c squared equals t.
And for simultaneous times according to S prime, use gamma t minus xv over c squared equals t prime. There's something else that I mentioned earlier, which I want to point out now. During the previous video on length contraction, we found a correlation between time dilation and length being contracted. In this video, the correlation between time dilation and the nature of simultaneity has become clear. But there is also a more direct correlation between the nature of simultaneity and length contraction. Let's take a look at this frame from the previous animation. First of all, note that we consider S prime to be stationary in this case. If we want to know the length of the spaceship, according to a spaceship observer, we would simply put a ruler on the screen and measure its length. That will be the spacecraft's actual length or own length. If we want to find out what an Earth observer would measure the spacecraft's length to be, consider these things. At this moment, the reference point would be located right here, and the spaceship's time at the spaceship's reference point would be 0.51 seconds. Now, to be able to measure the length properly, we would have to know where the exhaust of the spacecraft is at the same moment in time for us on Earth. If we draw a line from the exhaust, we find that the time at that point is more than what we found the time at the reference point to be. We can interpret this as the rear of the spaceship, the exhaust, having traveled farther in time than the reference point. That means that the exhaust has also traveled further in distance than the reference point. So the total spacecraft would have to appear shorter from the Earth's point of view. We'll set the display with the slanted line aside for now. The next situation is not the same as the previous, but it's similar. Let's view this other situation from the Earth's perspective. The spaceship flies by the Earth, and both spaceships' clocks are synchronized by a system within the spaceship. From Earth, we only know that our clock and the spaceship's left clock start at the same time. If we measure the spacecraft's length when our clock starts, we would put the left side of the ruler at the exhaust and the right side at the tip. We'd want to read the measured length at the same time, which would be according to this ruler. Now, if we were to see a spaceship observer measure the length, we would see them put down a ruler at the exhaust at time 0 seconds, but we'd see them read the end of the ruler a lot later than 0 seconds. Both moments would be simultaneous to the person in the spaceship though. So how much shorter would the spaceship appear to us? Well, if you look at the picture we see here, you would be right to conclude that the factor of length contraction seems different than the 0.8 that we've been working with. Let's work out that ambiguity in the next animation. But before we look at the next animation, let's note the times we see at both ends of the spaceship. So the left clock is at 0.3 seconds and the right clock is at 0.0 seconds, or where the clock is about to start. In this display, realize that the length of the spaceship is its actual length and the distance between the Earth and satellite is contracted. Now picture that we are located on Earth and there is a person in the spaceship who will help us conduct an experiment. For this experiment, we will need to fill up the area between the Earth and satellite, and we'll do that with a wooden beam, like so. Next, we will ask the observer in the spaceship to put a stake in the Earth's frame of reference at the left clock, when that left clock is showing 0.3 seconds. And we also want him to put another stake in the Earth's frame of reference at the right clock when it is just triggered to start, so at 0 seconds. Let's see how that would look. Now realize that the space between the stakes that we are currently looking at, let's call that delta x prime, is a certain length in the moving frame of reference of the Earth. If the space observer wants to know what that distance is to an Earth observer, let's call that delta x, he will have to multiply his own delta x prime by the scaling factor that we are currently looking for. We will call that factor a for now. So that means that delta x prime multiplied by a equals delta x. or the distance that an Earth observer would see between the stakes. In other words, the length that an Earth observer would see the spaceship to be. We also know that the scaling factor needs to work both ways, symmetrically. This means that if we multiply the observed length of the spaceship, observed by Earth that is, by that same factor A, we should get the actual or true length of the spaceship, L. If we combine those two multiplications, we will get the following. Delta x prime multiplied by A squared equals L. Now let's look at the spacecraft and the locations it is at, according to himself, when the stakes are inserted in the beam or in the frame of reference. We can find out what the distance between the stakes is according to him in terms of length L. That way we can find a direct relation between L and delta x prime and thus find the scaling factor A. Going back to the insertion of the right stake, we find that its distance to Earth is a spaceship's length L, because we decided that the time of 0 seconds occurs when the left part of the spaceship passes by the Earth. Let's look at when the left stake is inserted. The time at the left clock is now x prime v over c squared more than when the right stake was inserted. If we want the distance from that point to Earth, we will multiply that time by v, which gets us x prime v squared over c squared. But what should we fill in for x prime? Well, that is the difference in x prime values between the two spaceships' clocks, or length L. So the distance from the left stake to the Earth is L v squared over c squared. Then what is the distance between the two stakes? Let's subtract the distance of the closest stake from the further. So L minus L v squared over c squared, which equals L1 minus v squared over c squared. Remember that what we have just found is equal to delta x prime. So let's fill that into our equation with the scaling factor A. L1 minus v squared over c squared multiplied by a squared equals L. Now divide both sides by L. Now divide both sides by the contents of the brackets, and let's take the square root. This shows us that A is equal to the square root of 1 over 1 minus v squared over c squared. And we have found this value of A before, and we called it gamma. So now we can conclude that LO is equal to L over gamma.
Going back to the animation of the Earth's perspective, first of all, take a second to look at the mentioned distances and the spaceship's reference point. We can look at the moments when the spacecraft's left and right clocks are equal. Let's use 0 seconds. We find that its left side is over the Earth, while its right side is over the satellite. That means that, according to the spaceship, its length is the same as the distance between the Earth and satellite. While to us, it is the distance between the Earth and the satellite divided by gamma squared. Because, according to us, the distance between the Earth and satellite is a factor gamma greater, while the spaceship seems a factor of gamma smaller. Now altogether it seems that we have found the factor for length contraction while only using the formulas for simultaneity. While in actual fact we still had to use the relations for time dilation to end up with this result. There is no length contraction without time dilation or differences in simultaneity. And there are no differences in simultaneity without time dilation and length contraction. The areas of space and time are apparently so connected, and that is why we call it space-time.